explore the distributions of the various columns and see how they are related to the target column. And they will often give you a lot of interesting insights about the data. They will give you ideas for whether you need to transform certain features, whether maybe there is some invalid data that you need to fix, whether you can combine multiple features to create new features, whether you can maybe do a logarithm of a certain feature to get a better correlation, etc., etc. There are many ideas that you will get as you explore the data. But today, because our focus is on logistic regression, we'll do a limited amount of EDA. So let's just install these libraries, these plotting libraries, matplotlib, seaborn, and plotly. And first of all, I'm just going to look at the location data. I'm going to see what different locations we have and how many measurements we have across locations. So I believe we have around 29 locations, if I'm not wrong. Let's check that. So rawdf.nunique, that will tell you how many locations we have. rawdf.location.nunique will tell us that, okay, we have 49 locations. So these are the 49 locations. Maybe there are a few more, but for these locations, you can see for each location, we have about 3000 values, roughly speaking. And that makes sense. 10 years of data. So per location, 300 or 360 days of data. Maybe it's not 10, maybe it's 9.5 years. So 300 rows of 360 days of data per year multiplied by about 9 years or 9.5 years should give us about 3000 values. But you will see that for certain locations, the number of measurements is smaller. Maybe they did not have weather stations earlier, they got weather stations recently, or maybe just data was not collected or was lost for certain days. So that's what this tells us. We're getting a good sense that we have mostly uniform distribution of data across locations. I have also chosen color as rain today. So we have split these bars to show whether the value of rain today is no or yes. So if you roughly look at this, you can see that in Albury, there were 2300 rain today, 2300 measurements where there was no rain on those days. And there were 600 days where there was rain on those days. So 600 out of 30,000, out of 3000, that's about 20% of days. And that seems to be roughly the case, that about 20% of days in pretty much every city, there was rain. And then for about 80 or 75% of days, there was no rain. Of course, that's not true everywhere. For example, here with Uluru, you can see that there are very few days where there was rain. And there are other, like Hobart, where in this case, you can see that there are quite a few days where there was rain. Or I guess this is Walpole. Yeah, on Walpole, there are quite a few days where there was rain. Almost 1000 out of 2500. Okay. So location definitely seems to be a factor that decides how much rain there is going to be. So there is some correlation here for sure. Let's look at a few more and we'll go through them very quickly. Let's look at the temperature at 3 p.m. So we're going to plot a histogram of what the temperatures at 3 p.m. look like. And let's also break those histograms by whether it has rained on the next day or not. So my guess is that if the temperature at 3 p.m. today was low, then it's likely that it might rain tomorrow. And this histogram seems to validate that. Like if we just look at the overall histogram, it seems to form a Gaussian curve or a normal distribution. But you can see that the red indicates the cases where it did rain tomorrow. So you can see that there are more cases of low temperatures and rain tomorrow than there are with high temperatures and rain tomorrow. So if the temperature is lower, it seems more likely that it would rain. Although there are still a decent number of examples where the temperature has been high and it has still rained, right? So this is how you can break down histograms specifically for classification problems. You can use this color argument I'm using Plotly here, but you can, or Plotly Express, but you can use Seaborn and there you have the hue argument. So you can use the color argument to distinguish between classes. And here I'm just getting a sense that when the temperature is lower, the chances of rainfall might be higher. Maybe let's also look at rain today. Let's also look at the distribution of rain tomorrow. In how many cases is rain tomorrow set to yes? In how many cases is it set to no? So it seems like out of 140,000 data points, for about 110,000 data points, it seems like it did not rain. And then for about the remaining 30,000 data points, it seems like it did rain on the next day, right? So this is called class imbalance. You have two classes, no and yes, and you do not have an equal number of observations in each class. This is an important factor we'll talk about later when we build our models. One other thing we have done here is we have chosen rain today as the color. So what does that tell us? This tells us that there were 92,000 instances where rain today was no and rain tomorrow was also no. And there were only 16,000 instances where rain today was yes and rain tomorrow was no. So that means if it did not rain today, then there's a pretty good chance that it will not rain tomorrow. On the other hand, here you see a mostly even split, which means that if it did rain today, if rain today was yes, it may or may not rain tomorrow. And if rain today was no, again, it may or may not rain tomorrow, right? So predicting rain tomorrow, yes, is difficult, but predicting rain tomorrow, no, is easier when rain today is no. Okay, so there are many ways to think about and interpret this chart. So spend some time on each chart trying to understand what it represents. But as such, we can already tell that if it did not rain today, we can be confident that it is not going to rain tomorrow. Of course, there are a lot of other factors involved as well. Then here's a scatter plot of maximum temperature and minimum temperature. So you can see on most days, this is what the distribution of maximum temperature, minimum temperature looks like. In fact, between them, there is a linear correlation. So you could probably even try a linear regression model to predict maximum temperature using minimum temperature. And you would have a line like this. But that's not what we're doing here. What we've done is we've colored in these days or these points using rain today. And you will start to see that the cases where the minimum temperature and the maximum temperatures are very close, right? Or where, first of all, the minimum temperature is low. And second, the maximum temperature is close to the minimum temperature where there's not a lot of variation. In those days, rain today seems to be more common. So when it rains on a particular day, then the variation in temperature is small. And maybe that is also relevant for whether it rains tomorrow or not, right? So these are all different facets that you can explore about weather. Weather is infinitely complex and weather has a lot of different interesting things that you can learn from. And then here is a graph of temperature today versus humidity today and how that relates to whether it rains tomorrow. So I'm guessing that if the temperature today is low and the humidity is high, then there's a high chance that there may be rain tomorrow. And that seems to be the case. You can see here that if all the red points are in the low temperature, high humidity region, and the blue points are in the high temperature, low humidity region. Okay, so try and make your own interpretations from these charts and try and visualize all the other columns of the dataset and then study their relation with rain today and rain tomorrow as well. But we will move ahead. So at this point, let us just save our work. So from time to time, you should be saving your work, and you can do this by importing the Jovian Python library and running jovian.commit. And the reason you should do this is because if you step away from the Google Colab notebook for 10 or 15 seconds, then the notebook will shut down and you can lose your work. So when you run jovian.commit, you will be asked to provide an API key. So this is not the Kaggle API key. This is a Jovian API key because we want to take a snapshot of this notebook and put it on Jovian. So you just open up jovian.ai. And in the Get Started tab of your profile, you will be able to find this API key. So just click on API key, come back here and paste it in. And what this will do now is this will capture a snapshot of all the code execution that we have done so far and take that Jupyter notebook and put it on your Jovian profile. So as you can see here, this is my personal copy of the lesson notebook that I've been working on so far. And any changes that you've made will be preserved here. And you can always go back to jovian.ai and you can find it in the notebooks tab of your profile. As you can see here, Python sklearn logistic regression. I have a notebook here just for this. And if you want, you can go back and you can click run on Colab or run on Binder to run this notebook. Okay, so do keep running jovian.commit from time to time. All right. Now, there is one other optional step that I would like to suggest when you're working with massive data sets where you have millions of rows. We don't have it right now. We have 100,000 rows. That's fairly small, relatively speaking. But if you have millions of rows or tens of millions of rows, it's always a good idea to initially work with a sample. And by a sample, we mean a fraction, a randomly picked fraction. And this is so that you can quickly set up your model training notebook so that each line of code that you execute runs quickly and you're able to just try out many different ideas very quickly. So if you would like to work with a sample,